Hello and welcome to Diplomatic Derivatives. In this series of lectures, we continue with applied mathematics, specifically vector algebra. Now, in terms of vector algebra, we have already covered multiple concepts, including position vectors, vector addition. We have talked about scalar and vector product, cross product. We have already talked about the topics in relation to scalar triple product and cross triple product. So you can check those videos out. The link is in the description box or the I button above. Today we are going to move forward to the next major topic in vector algebra, that is differential operators. So in differential operators, we're going to start with the basic concept, which is about gradient of a scalar field. Because using this concept, we will be moving forward towards divergence of a vector, curl of a vector. Those are important concepts in CSS. So first, we will focus on the base of those concepts, that is a gradient of a scalar field. So let's see what is a gradient. Alright, so now before we move on towards the gradient of a scalar field, first we'll talk about the scalar field itself. So what is a scalar field? We know that scalar is a quantity which has only magnitude and no direction. Examples of scalars are temperature, pressure, and density, right? Now, what is a scalar field? Basically, a scalar field assigns a scalar value to every point in space. So if you have a certain point, let's suppose if you look at this space over here, and if you talk about temperature, let's suppose, right? So at every point of that space, somewhere, let's suppose here you have a certain temperature, here you have a certain temperature, here something else, and so on, right? And it depends upon the distribution. So it depends if the temperature is rising, if the temperature is decreasing, and if for example, at this particular point, the temperature is according to the coordinate system x, y, and z. So that is the position, right? So here you have another xyz, here you have another xyz, right? So that's basically a scalar field where a temperature is basically distributed inside a particular space, okay? Okay, so now we move on toward the term gradient. Now we understood what is a scalar field, we see what is a gradient. If phi xyz is a scalar field and its gradient is nabla phi, this is read as nabla phi, or you can say gradient of phi. Okay, nabla phi is equal to del phi by del x, del phi by del y, and del phi by del z. That is basically the change of temperature or pressure or density, that is whatever the scalar quantity is, its change in the space. Okay, that is basically the gradient. All right, it produces a vector field. Now the change always happens in a certain direction, right? So for even if it's a vector quantity or a scalar quantity, whatever the quantity is, the change will always happen in a certain direction. Therefore, the product of the scalar, the gradient, that is basically gradient itself, is going to be a vector quantity. Okay, so the gradient of a scalar field is a vector field. That is the answer that you're going to get, is going to be a vector quantity. It shows how phi changes with respect to position. Okay, this is basically what a gradient means. Now, as a vector, is going to have a direction and a magnitude, right? So what is the direction? Direction of maximum increase. So always the gradient is going to be in the direction of increase, okay, where the thing increases maximum. So if this is a point and this is another point, so this is the arrow. Okay, the gradient arrow always points towards the direction where phi rises the fastest. Okay, it will always point in the fastest change direction. Magnitude is basically the rate of increase. So if the magnitude is large, it means there was a rapid change, and if the magnitude was small, it means there was a slow change. Okay, so for the answer that you're going to get, which is a vector quantity, there will be a direction and then there will be a magnitude. Now if you talk about an example, let's suppose if your phi is a temperature, right? If you're having a scalar field which is temperature, so del phi, that is nabla phi, tells where heat rises the quickest, okay, such as heat escaping a laptop. So it will always point in the direction where it increases maximum. Okay, Okay, so here now we're looking at a surface. Surfaces given by phi x, y, z is equal to constant are called level surfaces or isosurface. So basically, if you have any surface, the gradient, that is a difference in whether it's a surface, for the surface we're talking about temperature, or for the surface we're talking about pressure, or whatever the scalar thing is, the gradient is always perpendicular to contours or level curves. So for example, if you have a piece of paper, the direction of the gradient on that piece of paper for temperature or whatever the scalar thing is going to be always going to be perpendicular. Okay, this is what it means. Now we take an example and see how to solve questions related to gradient. And this the questions that the thing that we're going to solve now is just a basic thing that will be used in the main questions that come in the exams. Okay, so this is kind of a step in the bigger question. Okay, so let phi is equal to phi xyz is equal to x square y plus 3z. So you have a particular value given to you, a scalar field is given to you, okay, and that is x square y plus 3z. It is represented by this expression. Okay, now for finding del phi, that is finding nabla phi, we know that it is the partial derivatives, basically del phi by del x, del phi by del y, and del phi by del z, right? So how do we find del phi by del x? So basically you put this thing over here. So you're taking the derivative with respect to x, right? So for this one, it will be, for this particular part of the expression, you have x squared y. So when you're taking with respect to x, it will be 2x and y will be written as it is. Okay, plus this will become 0 because there is no x in here, right? So you will get 2xy. Next you will do del phi by del y. So in terms of y, x squared as it is, and derivative of y is 1. So you will have x squared plus this, there is no y, so it will become 0, so plus 0. And then you will have del phi by del z. So this does not have any z, so it is becoming 0 plus 3z. So for 3z, the derivative will be 3. Okay, so now you have del phi by del x, you have del phi by del y, and you have del phi by del z, right? Therefore, nabla phi is equal to, which is the gradient, is equal to 2xy, x squared, and 3. Okay, so very simple way of solving. We already know how to do partial derivatives, so you will just do the partial derivative, and this is just one step. This is a single step in the main questions that we will be solving in the future videos, okay, where we will talk about the next topic. So this is how you find the gradient. Okay, so that's all for this video. I hope the basic concept of a gradient is clear to you. It's a very simple concept. There is no rocket science here. The next topic that we'll be talking about is divergence and curl of a vector. And in that video, we will understand that what is a divergence, what is a curl, and how we're going to use gradient of the field in this topic. Okay, so and then we'll also be doing some questions from the past paper, so you will be able to understand how to solve these concepts in the examination. All right, so that's all for this video. Make sure to like, share, subscribe to my channel, and wait for the next video. That's all for today. Thank you. Bye bye.